Students, we are going to start lecture number 13 today, and in this lecture we are going to first finish off discussions on decision tree or DT, and then we will start a new algorithm called support vector machine. So, this is a part of the getting started with ML models and their applications. I have been giving you examples of different kinds of applications. So, I will provide you some more details of the Python script in the next couple of lectures. So, we will learn today mostly about DT and SVM. Please keep in mind that. As you know, why we do need DT or decision tree? There is always, in the world there is always large varieties of materials, and their physical, mechanical, chemical or functional properties vary. So, how do you choose the best material for certain set of properties? Let us say mechanical properties. It is always a difficult decision for the engineer, right? And you need to make an accurate decision, and the accurate decisions requires a lot of efforts. So, can machine learning help us? Obviously, answer is yes. An intelligent automated solution is what is the need of the hour. So, what are the objectives? Because we need to create a decision tree model for the material selection based on certain index, which I will discuss further today, either a entropy or information gain or Gini index, and you have to place a Python application. Almost all the modeling is done by Python that can use the input or the data sets and then automatically select the material. Remember, the algorithm is DT. So, this allows us to find out the guidelines for the mechanical property based material selection. Remember, at the beginning of this course, I gave you some examples of selections of material from Michael Ashby's book, and there I provided you certain charts, what is known as Ashby charts, and that is very easy to do. So, therefore, this in a sense can allow us to bypass that chart thing and allow us to create new guidelines for mechanical property based mechanical selection, material selection process. And finally, we can actually study the model performance against some experimental data, so that we can validate the model. This is what I gave you, right? You can look at this data carefully once you see the video nicely. What we have is basically information chart for different kinds of materials, cost, different types of things like low, medium, high, relative cost, right? So, obviously, we can always give values, but values can vary from place to place, time to time. That is why it is better to provide relative cost. Strength can be always high, low, medium, and corrosion resistance can be two types, yes or no, and it can be lightweight or heavyweight or medium weights, right. So, you can make a chart like that based on your experience or based on the literature data and create a data sets. You can see that we have created huge data sets, almost hundreds of data. I am only providing you about 65 data sets in this table, right. So, now the question is, how do you make a decisions in using this chart? So, obviously, there will be always rule of the game, right. So, we have to follow certain rules, and these are the rules. Like steel is a high or medium cost elements, is a high strength, and corrosion resistance is not there, is a heavy weight, and similarly aluminum is also low medium weights, right. So, composites also there, plastics and titanium. Titanium is high corrosion resistance, composites also high corrosion resistance, and including plastics, remember this. Now, the question is, decision can be easily made by making a tree like structure. So, here I shown you strength as the root of the tree, you can see that, then you have branches out in different ways. So, I do not want to get into details, here it is shown nicely, you can see the low, medium, high strength. This is the example I gave you. Second example I gave you is what? Weather, right. There are 14 days of weather forecast and whether you will play tennis or not. So, basically each input has 4 categorical features: outlook, temperature, humidity and wind, and we have to make a binary classification problem, whether you play tennis or not, yes or no type. That is what it is. We can make also a table, right, like outlook can be sunny or rainy and then followed by. So, decision tree is what? Here one can actually approximate discrete value target functions. That is the primary important thing you have to understand, right. So, learned function is represented by decision tree. We are using a tree like structure to make a decision, and it can be represented as a set of if and then rules, because we can always understand readability. This is robust to all kinds of noisy data and capable of learning distinctive expressions. Remember, this was discovered by Payman et al. In a groundbreaking classification regression tree analysis, what is was a cut in 1986, and that is why then again it is widely used for various kinds of purposes. Material science is widely used. This is one such structure, and you see here there is a root node followed by decision nodes, what is called intermediate nodes, and then you have a leaf node where these things are ended, right, decisions are ended in leaf nodes. So, data are split here in the decision nodes and things are ended in the leaf nodes. So, decision tree is typically a divide and conquer approach, remember this, and it is basically subcategorized. It is divide and conquer means what? It subcategorize the data into different parts, and that is how we can make good decisions. It is a tree like structure and it composed of modes and many other things. I will talk about it. And very important characteristic, I already told you about these aspects. So, it has a root node, you can see here there is a root node. So, root node, how root node will be decided, I will talk about today now, and then you can have what is known as an internal node and also a leaf node. So, the internal node we can also call as a decision node, right. So, root node is where it starts, the tree starts at the root node, then you have an internal node or decision node where the decisions are made or data are split, and third thing you have is leaf node where the tree ends. So, root and internal nodes test the rules. All the rules I talked about just a couple of minutes ago, they test the root, and leaf node makes the predictions. So, you understand that this is what the structure of decision tree, right. So, here you have done mammals based on body temperature, warm or cold, and warm has two parts. It can either give birth, then we can call a mammal. It does not give birth, then it is called a non-mammal, right. So, there are a lot of non-mammals like snakes are things that do not have give birth. The kids comes out of eggs or something. It also includes turtle or even other animals also, right. So, but like human like animals or monkeys, they have they give birth, that is why they call mammals, right. This is a very simple example where we can explain root node and internal node and the leaf node, right. So, algorithm what you use basically known as a greedy algorithm. Let me tell you, basically we are dividing data based on certain rules, right. So, it always use the approach what is called as a greedy approach, and T is constructed in a top down recursive manner. What you do is basically divide and conquer. You divide the data in different parts. So, at the start we basically put all the examples at the root, right, and attributes basically categorical, they are mostly discrete actually. Even though they are continuous value, they are discretized in advance also, and then test attributes are selected based on the basis of certain manner like entropy or information gain or Gini index. So, how do you do the stop partitioning? All samples of a given node belong to the same class, right, like mammals, they are hot blooded, okay. There is no remaining attributes for further partitioning. You can always apply majority voting. I discussed you about majority voting couple of class before also, and we can also stop when there is no sample left. So, if you keep on dividing and you go to the end, there is no further things left for dividing, then also you stop, or you can also go by majority voting also when sample, right. This is how it is done. So, main question is that how do you construct and how do you divide the data? That is why I actually use several kinds of formulae or several kinds of functions. One is the information gain, second is called entropy, and third is called Gini index. Okay. So, what is information gain? It is a quantitative measure worth of an attribute. What is that? How well a given attributes or feature separate the data to different classes. That is what information gain tells you. So, basically it measure expected reduction in entropy. So, first you should know what is entropy. Let us talk about entropy now. Very important thing, you have to understand what is entropy, and entropy is always, what is entropy? Entropy is always used for what? To separate data. So, I will go back to the board and explain to you what is entropy in a very nice manner, so that you do not forget it. Okay. Because entropy is widely used in physics or material science and many other things. So, entropy is something which you have to understand very well. So, first parameter is entropy. So, entropy is a very basic in physics chemistry. It is a quantitable mathematical factor. So, we write entropy like this. Okay. You can see that. So, this is sum it over I 1 to n minus pi log 2 pi. Remember, this base is log 2. Okay. That is a different thing for other logs. Pi is what? Pi is always defined as a distribution. So, let us say I have binary classification. That means I have either yes or no, like in tennis play. So, yes I term as a p positive, no I term as a p negative. Okay. So, I can write down entropy then as minus p plus log 2 p plus minus p minus log 2 p minus, correct. So, these are the decisions made. Am I clear? Yes or no. To give an example, very simple example how it is used, I just noted down. Let me just tell you that. Let us say I have what? Somewhere down the line I wrote that. Let me see, what did I write? Very simple example, A, B, C, D kind of stuffs. Yes. Let us say I have a set S like this: A, B, 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 like this. So, there are 8 data points. So, total instances is 8. A stands for affirmative, B stands for negative. So, how many instances of A? 3. Instances of B? 5. Okay. Out of 8, 3 instances of A, 5 instances of B. So, what is the entropy then? So, I can write down entropy as set S actually is very simple. We will take minus out 3 by 8 log 2 3 by 8 plus, remember we have taken the minus out here, and 5 by 8 log 2 5 by 8. That is what is my entropy is. So, I have 8 total instances, out of which 3 are affirmative A and 5 are B negative, right. So, if you calculate properly, this will be equal to minus 0.53 plus 0.424. So, remember this is a fraction 3 by 8 or 5 by 8. So, therefore, log of that is in negative. So, finally, you get minus 0.954, right. So, I gave you example where there are two sets of instances, but if you may have many sets of instances. So, there you will have to use summation rule. For each you have to divide for each case how data are partitioned. So, PI means what? How data are partitions, right. We are partitioning data at each node, at each internal node or decision node. So, that partitioning number I should know. How many of the data belongs to a particular subclass? That is what I should know very well. That is what is known as a PI. So, that means PI is nothing but the fraction of data split in a particular node which correspond to yes or no or many other things. Okay. So, that is how actually entropy is calculated. So, hope you understand that. So, what does entropy tells you physically, correct? What does it tells you? It tells you that after every split, entropy must decrease, right. This S must decrease after every split, then only splitting is proper. If entropy keeps on increasing, that means your splitting is not proper. This is something you have to understand. Entropy will always decrease as you keep on subdividing the data. That is how you are doing, right. You are taking the root node, you are taking all the data, then you are splitting into decision nodes. So, finally, what you are doing it separately, separating out nicely in a tree like structure. So, entropy must decrease as you go along these aspects. So, this is about entropy, right. So, now let me talk about information gain. Okay, what is information gain? This is also related to entropy only. Information gain is also used since it indicates gain of information. So, it is self-explanatory, right. There is no problem when you talk about information gain. Is there any issue in information gain? All of you understand? No. Okay. Let me write down the equation, that is what is very important. So, suppose I have a set S, okay, and set S, it has set of instances, set of instances, yeah, instances means data, right, A. Now, S is then, I create a subset, SV is a subset of S, correct, and I create this subset from S by using this attribute A, very simple, like you have outlook and then you have two important things, sunny, rainy. Am I clear? Then you see that from rainy you can have wind, right, low or wind high, and then you have another thing called overcast. Please go back my slides. Sunny can also have humidity factor, right. So, what I am saying, this each one is this is an attribute, this is an attribute which is splitting the data. So, this set S which is at the root outlook, this is what is the set root node, this set S is split. We create a subset SV, this is one, this subsets, right, using this attribute. That is what I am trying to say. So, then the gain, because you split the data using the attribute, you create a new subset from the S. Gain is nothing but entropy, original entropy S of the data, this entropy S, entropy of this set of data, minus we can write down SB by S mod entropy of SB. In a very simple way, this is what we can write. Obviously, one can write this also, correct, because we have used attribute A, split the data from S to SB. So, we can write down. So, basically what we are doing, we are creating a new subset from the original set. From the original set S, we create a new subset called SV, and we are trying to find out if I do this, what is my gain. So, therefore, initially I have entropy of this substrate, okay, entropy of this substrate, remember, and I am subtracting this one when I create a new subset SV, what is the kind of entropy, and at the same time I am multiplying with this ratio SB by number of elements in SB divided by number of elements in S, right. That is what I am doing. So, this is what is known as information gain. Remember this is not same as, and this is more important than entropy. This is widely used in entropy. This is more widely used than entropy actually. That is why information gain is very important. So, let me give an example and show you how it is done. Okay. So, one of the way of looking at decision tree is, where is that? Okay, we will come back to it a little later. First, let me explain the third one. Okay, I think I have this example in my slides. So, this is what is called information gain, and third one is called as a Gini index. Okay, Gini index. This is the third one. This parameter is used to split the data. What is Gini index? Basically, Gini index talks about Gini, or it is called Gini impurity also. Okay. It is somewhat similar to the entropy, but not exactly entropy. So, Gi, that is what is short form of Gini index, that is equal to 1 minus sum it over I going to 1 to n pi square. Remember pi I used in entropy. Entropy is what? Let me write down entropy here. Okay. So, entropy S is nothing but sum it over minus I to n pi log of 2 pi. So, this pi is nothing but partition of data. Here we are not using a log, but we are basically sum it over pi square. Pi can be actually a very small fraction number, that is why, and then you subtract it from 1, right, that is what we are doing. So, if I expand this for this case, for the binary classification case, it will be 1 minus p positive square plus p negative square, okay, for a binary classification case, very easy, yes and no type cases. Am I clear? So, for this set which you did, right, A, B, 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 okay. So, we can always write down this Gini index Gi for this set is what? 1 minus, so what is the positive case? 3 by 8 whole square, and that is 5 by 8 whole square, A and B, right. So, similarly you can do this 1 minus, so 9 by 64 plus 25 by 64, that has become 1 minus, so 64 34, so that means what? It is basically 30 by 64, that is what is a Gini index is, right. So, you can easily calculate this way. So, there are 3 parameters I discussed, one is entropy, second is information gain, and last one is the Gini index. So, Gini index and entropy are similar. So, let me just go back to the slides and explain to you what is that you want to do, right. Then we stop this thing. So, these are all aspects I discussed, okay, information gain, everything, let me not go back. So, yeah, this is the example I want to say. So, talk about this weather problem, 14 days weather data. So, you have calculated gain. So, let us say I calculate gain of the set S in terms of outlook. Outlook is one of the attribute or feature use, and if you do the calculate, you will see this, if you use outlook as a root node, the value of gain information is 0.246. If I use humidity, is 151. If I use wind, it is even much lower, temperature even much lower. So, very clear information gain is highest for outlook. That is why it is used as a outlook as a root node, correct. Now, one can actually branch it out. You can see that we have branched it out sunny, overcast, rainy, right. You can remember that. So, you can calculate gain for sunny d1, d2, d3, these are the different parameters. Sunny and humidity is about 0.970, correct. Sunny and humidity is one branch, right, you remember that. So, like go back and show you that if you forgotten. Yeah. So, you can see sunny, humidity is high or low, right. Outcast, overcast, yes. Rainy, you have wind speed strong and weak, right. This is what is your decision tree, but how do you select the outlook as the root node and these are the decision node, that is what we are discussing, right. Let me go again further and explain you. So, root I explained to you, the gain is highest for the outlook, that is why root is used outlook. Now, you separate the data in terms of sunny, overcast, rainy. If you consider sunny and humidity, your information gain is highest 0.970. If you use sunny and temperature, it is lower 0.570. If you use sunny and wind, it is even much lower. So, very clear sunny and humidity is a better dividing or splitting factor than anything else. Now, if you take humidity, you can clearly see if you use a high, there are 3 positive, 4 negative. So, therefore, gain is what? Gain is 0.151, but if you use normal, then it is 6 positive and 1 negative. So, E is become 0.592. It has much higher information gain if you divide the data this way. So, wind speed also you can do the same thing. You go back to the chart I provided and there are 6 positive and 2 negative data, yes and no basically, and then you can calculate gain for wind, weak wind, you can see is 0.058, but for the strong winds is 1, both negative and positive cases similar. Okay. So, that is how actually one can distribute the data or create the decision tree very nicely, right. Well, this is for you to check, but machines will do very easily these calculations and it can handle even much larger data sets. Okay. That is what I wanted to tell you for the decision tree aspects. These factors, remember, entropy, information gain and Gini index is to be considered. Okay. So, the TS will discuss about how this Gini index can be used as one of the features, one of the factors for calculating data for the example of steel or aluminum thing I given you, right. So, let me stop here, I come back to the next part of lecture and where I discuss more about SBM or something, right.